Okay, sir.
Okay, we will start today's presentation. Now, before we do today's presentation, we will simply make a brief presentation of what we have been trying to do. We have been trying to do three things. Okay, one is we know very well the electrochemical systems are converting chemicals into electrical energy. That is the thing. So there are various types of cells and other things we have already seen, various types of electrodes and other things, all those things, and there are conventions about it. We will see little later also again when we do all the electrochemical cells configuration. Now from there we went where electrochemical cells are mainly essentially electrode and electrolyte. So therefore we will look at the models of a electrode electrolyte. There are various models, out of which we have taken only 4 or 5 models. One is the one is the capacitor model, another one is diffuse double layer model, Stern-Chapman model, and then the Devanathan-Bakris model is what we saw. But all these models are ideal models. None of them are really replicating the actual situation in practice. Now, from there we went to semiconductor electrolyte interface and showed that the field penetration is even within the semiconductor, and it has a consequence. Now, what we are trying to do is we are trying to look at the general concepts of electrode kinetics, because after all, the photoelectrochemistry or any electrochemical systems, the electron exchange at the electrode is going to be the main process, and the kinetics is controlling the current that we can do, or controlling the power that we can draw. So we are trying to look at that. Okay, that is what we are trying to do. Then when we are doing this way, when we are measuring the current as a function of potential, we have already seen that applying a potential on an electrode is polarizing the electrode. That is all. This is a question we have been always asking thing. Now the extent of polarization can be different because of the magnitude of the potential that you are applying. Anyway, we will not going back on that. So when we are measuring current as a function of potential, because these are the only 2 variables that are available, within this variable we will see concentration and other things which are usual variables for chemists. Now, if I were to take a potential versus current plot, what will happen is, up to a particular potential, the current will be very small, and after a potential, at a particular potential, the current will steeply rise, and the current will saturate at a certain potential. This is what is called the S-shaped curve. Now, this S-shaped curve is, we have to look at this the charging that is taking place in the initial thing, where there is no chemical reaction of the depolarizer, or there is electroactive substance. So therefore the charging is due to other reasons. The magnitude of the charging is higher in this and lower in this. We will not worry about it. So what it means is, whenever I have IE curves recorded at much higher sensitivity than in figure 1, so when we have note that due to the presence of electrical double layer, a charging or capacitance current is always present in voltammetric measurements. So this is what we are talking about. This is the charging current, and this is the limiting current. In this case, this is the limiting current, and the concentration of the species must be proportional to the charging current minus limiting current minus the charging current. ID minus I charging current, or the magnitude of ID. So now, when we take this is all taken from the blue transparencies or blue projections are taken from literature because they are better describing certain things. That is why we have taken as such the projections we have taken from them. We could have made our own projections, but it is more. So what we are looking at it is copper dissolving as copper 2 plus ion, or copper 2 plus ion getting deposited as copper. Okay. The same way, if I were to look at the other species, Fe3 plus, Fe2 plus going to Fe3 plus, or Fe3 plus going to Fe2 plus. So these are the two different things. So now what we are measuring is the net current. That is what we are measuring. Oxidized species plus electron give you raised to reduced species. So therefore, the cathodic current, anodic current. Cathodic current is the intrinsic rate constant in the concentration, all those things, that is equal to IC by NFA. Then in terms of the current, okay, the rate of cathodic reaction, rate of anodic reaction, IC by NFA or IA by NFA. IC is NFA into Kc into concentration of the species at 0 time. Okay, IA is also the same way. So what the current that we measure is IC minus IA. That is what we call as the NFA into Kc into C oxidized species minus Ka into C reduced species. This is the simple kinetics, the equation that we will write generally. So now, if we have to look at this, the potential energy curve or potential energy surface is what we should do. But anyway, potential energy curve is enough. So all these things we have studied in the simple kinetics. Therefore, if we do this, if it goes like this and if it goes like this, then it is a symmetrical peak. So the Kc will be the intrinsic rate constant to Kt by h e to the power of the minus delta G cathodic by RT. The same way, Ka, the intrinsic rate constant for the anodic reaction is equilibrium constant into Kt by h e to the power of minus delta G A by RT. All these things we have studied. When Kc is equal to Ka, then it is called the here we have defined again the standard exchange current. I net is equal to 0, IC is equal to IA is equal to I0. So I net, IC minus IA is equal to 0. Under those conditions, what is the current measured in IC or IA is equal to standard exchange current density. The net current IC minus IA will be 0, but I0 is not 0. I hope you understand. I net is equal to 0, but IC is equal to IA is equal to I0, which is the exchange current density or exchange current. So now here I have shown it in the terms of the potential, in the terms of the extent of oxidation and reduction reaction. Now if the red line shows the oxidation current, the solid line is the reduction current. If the magnitude are same, then Na going to Na plus and plus electron. So then this is the Ia will be equal to Ic, or Ia anodic oxidation is equal to current to the cathodic reaction. So now if the magnitude of the anodic reaction and cathodic reactions are different, the anodic oxidation current is more, the cathodic reduction current is less, then this type of potential distortion will take place. In the same way, when the anodic current is low and the cathodic reduction current is more, the potential energy curve will now be this. The energy levels of the species in solution keeps unchanged, while that of the species on the electrode changes with the electrode potential. Okay. So therefore, the same thing is shown here, but in a different thing. The oxidation reaction, the reduction reaction are shown here in the picture. We will see later on all those things. All these things are the equations of necessary for these things, which we will be dealing with separately again. So now these are all from the literature, so we will not worry about it. We will take it up later on. So now we have already talked about it. The current I is the current, not the current density. Current is equal to A, area of the electrode, I0, exchange current density, into exponential 1 minus alpha NF by RT into E minus E equilibrium, minus exponential minus alpha NF by RT into E equilibrium, E minus E equilibrium. So I is the electrode current, okay, in amperes. I0 is the exchange current density, amperes per square meter area electrode. E is the electrode potential here. E equilibrium is equilibrium potential. A is the electrode active surface area. We have to look at what is this active surface area and the electrode area later on, and how to determine the active surface area. T is the absolute temperature. N is the number of electrons involved in the electrochemical reaction or electrode reaction. F is the Faraday. R is the universal gas constant. Alpha is so-called symmetry factor or charge transfer coefficient, which is dimensionless. The equation E is named after chemist John Alfred Valentine Butler and Max Volmer. While the Butler-Volmer equation is valid for the full potential range, okay, I hope you are here the potential range we are talking about x-axis, the potential range, y-axis is the current. So anyway, we will not worry about it. So therefore, it is applicable to the whole potential range. While Butler-Volmer equation is valid for the whole potential range, simpler approximations solutions can be obtained for over more restricted ranges of potential. We will see that in a picture. You see, if the variation is going to be, for example, if the anodic reaction is current is like this, the cathodic reaction is this, in this potential range up to this, you can see that it is linear. The same way from this to up to this, it is linear. Okay, potential is the x-axis. So therefore, what it means is, as over potentials either positive or negative becomes larger than 0.05 volt, the second or the first term of the equation becomes negligible. Okay, if this term or this term will become negligible. We will see when it will be. Hence, a simple exponential relationship between current and over potential are obtained. When we have, suppose if this is zero, negligible, then the current will be proportional to this term. Okay. So hence a simple exponential relationship between current and over potential are obtained, or over potential can be considered as logarithmically dependent on the current density. This theoretical result is in agreement with the experimental findings of the German physical chemist Julius Tafel, and the usual plots of the over potential versus the logarithm of current density is known as the Tafel lines. The slope of the, we will show that again. The slope of the Tafel plot reveals the value of the transfer coefficient for the given direction of the electrode reaction. Because when we say this term is zero, then it is an anodic reaction. If this term is more than this, then this is a cathodic reaction. So therefore, IA is I0 exponential alpha 1 minus alpha NF eta A by RT at high anodic over potentials. IC, the cathodic current, is I0 exchange current density exponential this at high cathodic over potential. These equations can be rearranged to give the Tafel equation, which was obtained experimentally. IA and IC are the exchange current densities for the anodic and cathodic reactions. Exchange current densities. So therefore, how to derive these equations are shown here. We will see later on all these things. The equation are not so, derivation of the equation is not so important at this point. The equation is a well-known Tafel equation, and that is the over potential is related to the logarithmic of the current, logarithmic of the cathodic current or anodic current. So therefore, the A in this equation is given by this. Okay, B is given by this because of the Butler-Volmer equation in two terms. The Tafel slope as is an intensive property. Intensive property, I hope you have understood it. Intensive property means mass dependent, does not depend upon the electrode surface area. I0 is and its extensive parameter and is influenced by the electrode surface area and kinetics or the speed of the reaction. Notice that the Tafel slope is restricted to the number of electrons n involved in the exchange in the charge transfer controlled reaction and so-called symmetry factor alpha. N is often 1 because we are always looking at the electrons are transferred as a sequence. Therefore, for any given step, only one electron maybe mostly is the one electron transfer. Although symmetry factor can vary from 0 to 1, it is normally close to 0.5. This means that the Tafel slope should be close to 120 millivolts if n is equal to 1 and 60 millivolts if n is equal to 2. These are all, we are going to have all these things. These are all the criterion that we should use for looking at the number of electrons transferred. The electrochemical electron transfer reaction is controlling all those things. These are all the very characteristic criterion for electrode kinetics. So eta is put like that. B is 2.303 by RT by NF. That is that Tafel slope. Logarithm I will be equal to. So this is what we have seen without consideration and therefore mass transport effects. To complicate the electrolysis, it is possible to establish the effects of voltage on the current flowing. In this situation, the quantity E minus E equilibrium reflects the activation energy required to force a current I to flow. I hope you understand. E equilibrium is the current is 0. E, the potential that we have to apply to get a considerable current, then E minus EI reflects the activation barrier or activation energy required to force a current I to flow. Plotted here 3 curves with values with differing values of I0 and with alpha is equal to 0.5. So you can see that C, B and A are E. This shows that the current is increasing this. So this corresponds to E minus E equilibrium. So you can see that this is the Tafel slope. Okay, Tafel equation. At this point, from this potential to this potential, it is linearly varying. Up this potential to up to this potential, the current is really linearly varying. So this is the equation. So the Tafel equation can be written as I will be equal to n of k exponential plus minus alpha f delta V by RT. The plus sign under the exponent refers to anodic reaction. The minus sign refers to the cathodic reaction. Plus minus we are talking about. N is the number of electrons involved in the electrode reaction. K is the rate constant for the electrode reaction. R is universal gas constant. F is the Faraday. K K or R. Okay. If K is used to Boltzmann constant, T is absolute temperature, E is electronic charge, alpha is so-called charge transfer coefficient, the value of which must be between 0 and 1, but mostly it is around 0.5. We have already seen this. So the following equation was obtained experimentally. Over potential is equal to A plus B logarithm of I, where eta is the over potential, I is the current density, A and B are Tafel constants. So applicability of the Tafel equation. Where an electrochemical reaction occurs in 2 half reactions on separate electrodes, the Tafel equation is applied to each electrode separately. If the same reaction is taking place on the anode and cathode, then we have to apply it to each electrode. The Tafel equation assumes that the reverse reaction rate is negligible compared to the forward reaction. Here, forward and backward is only a terminology. There is not a very thing. But what you are doing is Is it an anodic reaction or a cathodic reaction? The Tafel equation is applicable to the region where the values of the polarization are high. What it means is, I hope you understand this. You see, the Tafel equation is only applicable in this region, not in this region. So therefore, the polarization is very high here. When the E minus E equilibrium is very high. The Tafel equation is applicable to the region where the values of the polarization are high. At low values of polarization, the dependence of current on polarization is usually linear. Okay, I hope you are able to see the current is linearly varying here. Here only it is exponentially varying. This linear region is called the polarization resistance due to its formal similarity to Ohm's law. There are very many equations that are possible in the electrode kinetics. So they are applicable in the linear region of the Butler-Volmer equation at low over potentials in this low over potentials. These are all high over potentials. Okay, this is already 0.1. It is 0.3 here, whereas here it is very small. I corrected current will be equal to B by Rp, where B is the Tafel constant, Rp is the measured polarization resistance, delta E by delta I. Because resistance is potential by current. The exchange current is the current at equilibrium, that is the rate at which oxidized and reduced species transfer electrons with the electrode. Okay. In other words, the exchange current density is the rate of the reaction at the reversible potential, where the over potential is 0 by definition. For example, here the potential is E minus E. This is equilibrium potential. The E minus E will be equal to the equilibrium potential. So the exchange current is the current at equilibrium, that is the rate of which oxidized and reduced species transfer electrons with the electrode. In other words, the exchange current density is the rate of the reaction at the reversible potential when the over potential is 0 by definition, not polarization. At the reversible potential, the reaction is in equilibrium, meaning that the forward and the reverse reactions progress at the same rate. This rate is called the exchange current density. This is a fixed quantity for a given set of electrodes. The Tafel slope is measured experimentally. However, it can be shown theoretically with the dominant reaction mechanism involves the transfer of single electron, that is B will be equal to 2.303 by RT by alpha F, where we substitute all RT and F and alpha as 0.5. Then we will see that it is when you substitute this and get the value of B, then it is, then we can say that the single electron transfer and the charge transfer coefficient is 0.5. There are various, as I told you, there are various equations that are possible in electrokinetics. Only one of them we are going to see. The Levitch equation models the diffusion and solution flow conditions around a rotating disk electrode. This is the reason why we are talking about it, because sometimes you are doing the rotating disk electrode measurements. It is named after Levitch, who first developed the rotating disk electrode as a tool for electrochemical research. It can be used to predict the current absorbed at a rotating disk electrode. In particular, the Levitch equation gives the height of the sinusoidal wave observed in rotating disk voltammetry. We have already seen that the current versus potential curve will be sinusoidal. So in particular, the Levitch equation gives the height of the sinusoidal wave observed in rotating disk voltammetry. The sigmoidal wave height is often called the Levitch current. In work at a rotating disk electrode, the electrode is usually rotated fast, okay, 1000 RPM or more, in order to establish a well-defined diffusion layer. We will just now show you a picture about it. The scan rate, okay, is relatively slow. This is the rotating disk speed. The scan rate is how you are measuring the potential. We have already shown, or we are going to see in cyclic voltammetry, the scan rate, the potential variation with respect to time is nearly 50 millivolts per second or something like that. Whereas in the rotating disc electrode, the measurements or scan rate is typically low, so it's slow, typically 2 to 5 millivolts per second. It is important to remember that in order to determine the diffusion current, the mass transfer coefficient using voltammetry, excess inert supporting electrolyte must be present to eliminate the migration current. This is what we have already talked about it. We will repeat it. In all these measurements, migration current has to be avoided. Only the diffusion current has to be measured. So if I have to do that, what we have to do is that the species transferring to the electrode must be diffusion controlled. So what we will do is the experiments will be done using a very high concentration of the supporting electrolyte, so that the ions are migrating in the vicinity, in the presence of the inert ions which are not electrochemically active. Inert means you should not think that chemically inert. Okay, they are electrochemically within the potential range that we are doing. They are not undergoing any electrochemical reactions. For example, potassium nitrate. So the Levitch equation is written as IL, the Levitch current, is given by the constant N F A D to the power of 2 by 3 W to the power of half V to the power of 1 by 6 into C concentration. You will see what it is, and how we will see, and also give a reasoning why all these powers are Okay. Hello, all of you are there?
Yes, sir.
There was some problem with the internet, that is why we have to do that. So
Yes, sir.
just like we saw in the current voltage curves, especially for the electrode context, we looked at the Butler-Volmer equation. Butler-Volmer equation is applicable to the electrode, the reactions that are taking place at the electrode-electrolyte interface or at the electrode surface, let us assume. The measurements can be done not only at the potential versus current. We can also do this in various ways. Rotating disk electrode is one of them. So we will take it to electron. I will show you a picture now, little in a minute. The picture. So you can see this is the rod rotating disk. The red and black one is the rotating disk. And the rod is the center of the disk. The flow of the fluid is like this. The concentration at the electrode remains the same. This situation when you do the electrode rotating disk electrode. Whereas if you do in cyclic voltammetry and other things, we are going to do that little later. Then what will happen is they are different. We will see that. So therefore, it is important to note that the layer of the solution immediately adjacent to the surface of the electrode behaves as if it were stuck to the electrode, while the bulk of the solution is being stirred vigorously by rotating electrode. This thin layer of the solution manages to cling to the surface of the electrode and appears from the perspective of the rotating electrode to be motionless. This layer is called the stagnant layer in order to distinguish it from the remaining bulk of the solution. Bulk of the solution is, you can see the bulk of the solution is undergoing changes, whereas the stagnant layer at the electrode remains the same. This act of rotating drags material to the electrode face where it can react. Providing the rotation speed is kept within the limits that laminar flow is maintained, then the mass transport equation is given by the Levitch equation. Whereas in the cyclic voltammetry or any other polarography and other things, it is the diffusion current. So this is the picture of Levitch. This is the measurement of this. This is the reference electrode. This is the working electrode, rotating disk electrode. This is the counter electrode. So the three electrodes are put into a potential stat. We will see later on what is a potential stat and other things. Maybe you must know this. All your photoelectrochemical measurements must be made only with a potential stat with a three electrode system. Three electrode system means the individual potentials of the electrode with respect to the reference electrode is measured, whereas the reaction is taking place between the working electrode and the counter electrode. So this is the Levitch equation. Levitch equation of the RDE, which we have just now written, we are repeating that. Levitch equation takes into account both the rate of diffusion across the stagnant layer and the complex solution flow pattern. In particular, the Levitch equation gives the height of the sigmoidal curve wave observed in the rotated disk voltammetry. The sigmoid wave height is often called the Levitch current. You already told about it, and it is directly proportional to the anolyte concentration C. IL is directly proportional to C, whereas it is d to the power of 2 by 3 diffusion quotient, the rotating speed to the power of half, and kinematic, where W is the angular rotation rate of the radians per second, V is the kinematic velocity of the solution. The kinematic viscosity is the ratio of the solution's viscosity to its density. Kinematic means the transport, okay? So transverse viscosity. So current voltage curve at RDE will be like this. Forward and reverse traces are on top of each other. Okay, there are two curves here. When it is a reversible thing, you will get this. So if I were to measure the Levitch current as a function of the speed of the rotating disk, omega to the power of half, okay, omega to the power of half versus I, it should be linear. This is one of the criterion that we should use. So the least square feet is put that we will not worry about it. So it should be linear. Okay. So the linear relationship between Levitch current and the square root of the rotating rate is obvious from the Levitch plot. A linear least square feet of the data produces an equation for the best straight line passing through the data. The specific experiments is shown. The electrode area A was 0.1963 square centimeter. The analyte concentration, okay, of the electroactive substance is 2.55 into 10 to the minus 6 moles per centimeter cube. The solution had a kinematic viscosity of 0.00916 centimeter per second. After careful substitution of the unit analysis, you can solve for the diffusion coefficient D and obtain a value equal to 4.75 into 10 to the minus 6 centimeter square per second. This result is little low, probably due to the poor shape of the sigmoidal signal observed in this particular experiment. The kinematic viscosity is the ratio of the absolute viscosity of the solution to its density. Absolute viscosity is measured in poise. 1 poise is equal to gram centimeter minus 1 second minus 1. Kinematic viscosity is measured in strokes. 1 stroke is equal to centimeter square per second. Okay, because density is what we put gram per centimeter, so therefore it will become centimeter square per second. Extensive tables of solution viscosity and more information about viscosity units can be found in the CRC handbook of chemistry and physics. I hope you remember that. So we will stop here. We will take up questions, and next time we will talk about cyclic voltammetry. Now, if you have any questions, you can ask. We are sorry for the interruption in between, but that was due to the failure of the internet. Any questions, please?
Hello, sir. Hello, sir. Hello, sir. Hello, sir.
Any questions? Okay, maybe next time we will repeat this a little bit and then take it up further. because of the interruption in the middle.
Sir, one question is,
What is it?
my microphone has some problems.
Okay, here is a question. Does the kinematic viscosity in Lewis equation is also related to the angular frequency of the rotating electrode? It is okay. The question is correct, but the kinematic viscosity that is substituted in this equation is only a numerical number. That does not depend upon the omega, the rotating speed. Even though there may be a small change of the kinematic viscosity with respect to rotating speed. In this equation, the Lewis equation, the kinematic viscosity is independent of the omega. Any other questions? I do not know how many of you followed this because of the interruption, and also otherwise we will repeat it the Saturday this again.
But yeah, the equation are little difficult, sir. It will take some time to learn and ask questions.
You please type, we don't hear you.
Okay.
Nanda, are you asking some questions?
No, sir, I am
Slide
just
number
telling.
22,
No, no.
explain the current voltage curve of electrode reaction. Okay. Here, this is the picture you are referring to? Because are you referring to this slide?
Yes, sir. Yes, sir.
Okay. These are all only the theoretical curves. These are not experimental curves. This is only to show that high over potentials, the current is steeply increases linearly at very low over potential. That is, when E equilibrium is equal to E, then it is linearly varies. Whereas in high over potentials, the current will be varying only after a certain potential linearly. So this is all plotted for an ideal case. This is the curve C, curve A is very low over potential, curve B is intermediate over potential, curve C is the very high over potential. So if I have a very high over potential, then the Tafel plot must be only the over potential versus current. At very low over potentials, for those reactions, Tafel plot cannot be made. Okay, we'll see it on Saturday.